Welcome. Here is a little bit more spectral graph theory. I'm wrapping up a paper on the tree-forest ratio. So that was the starting point. How does the number of rooted trees and number of rooted forests behave in the barycentric limit? And it's interesting because there is a universal barycentral density of state, which in the one-dimensional case we completely understand, in the high-dimensional case we don't. And in order to estimate things, in order to show that the potential theoretical part, especially these numbers, exist in the limit, we need some estimates. And we need estimates on the eigenvalues. And I have used a result of Schur-Horn inequality, but it's actually better to use to make this a little bit stronger. And this is a result. I don't know whether it has appeared. I looked in all books and I didn't find it yet. It's quite an interesting general result on the eigenvalues of the Kirchhoff matrix of an arbitrary graph. So the result which I'm going to prove, so that's a pretty general result, a pretty useful result, because eigenvalues are important in graph theory. And let me just get started with a couple of definitions. I'm keeping it brief, but on the left hand side I have all definitions. We have a general finite simple graph like this one, and we have the Kirchhoff matrix, which is a Laplacian, which is the divergence of the gradient, and it has in the diagonal the list of vertex cardinalities, and in the side diagonals -1 if there is a connection. So it's B minus A, where B is the diagonal matrix and A is the adjacency matrix. So in this case, for example, for this graph here, the vertex cardinalities as a 1, 1, 1, 3, 3, 3, 4, 4, 4, 6. So this is a case, a specific example, and we can also compute the eigenvalues, and I can, for example, plot both. I can plot both the eigenvalues and this vertex cardinality multiplied by 2. And then you see that it is bounded above. So I saw that experimentally and made experiments with lots and lots of graphs, and it always holded, and so I tried to prove it, and I also tried to find it in the literature, and it's actually quite simple to prove. But so the eigenvalues are always ordered, in an increasing manner, and also the vertex cardinality are ordered in an increasing manner. And then we also look at the barycentric refinements. So in this case, when you look at the barycentric refinement, then you look at all the complete subgraphs. So in this case, there are vertices, there are edges, there are 4 triangles in this case, and there's 1 tetrahedron. And so when you make the barycentric refinement here, this tetrahedron becomes 24. Becomes already 24 tetrahedrons, so that grows pretty fast. So it's a 3-dimensional case. In any dimension, maximal dimension here is 3. There's a K4 subgraph, and it depends on the maximal dimension. So in the case 1-dimensional case, when there is no triangle, we have a situation like this. We see that the eigenvalues are nicely accumulating on the interval 0, 4. And actually the limiting density of states is that beautiful equilibrium measure, which one knows from dynamical systems theory, statistical mechanics, and so on. It's the the equilibrium charge on that interval. It's the interval of maximal entropy for the logistic map on that. The topological entropy is equal to the metric entropy. It's a very well-known situation. It's the arcsine distribution in probability theory. In high dimensions, we don't know what happens, and that's really kind of research which I'm trying to make progress. For example, there is a gap here, actually a pretty clear gap. You know, it looks like a contour set, but there's a clear gap, for example, between 4 and 6, but I cannot even prove that this gap exists in the spectrum of the limiting density of states. It's pretty interesting also from an ergodic theoretical point of view, because there are certainly here dynamical systems involved in some topological groups in the limit. Here it's the dyadic group of integers, and it's the group addition and the adding machine. That's what I did in my thesis, kind of essentially kind of worked on that as a special case, and here we have no idea what happens. We know this paracentric limit exists. In order to do the estimates we have to show that this density of states decays fast enough, exponentially fast. So here, usually what we draw is the, also in spectral theory of Schrödinger operators or whatever you are doing, we draw the Lyapunov exponent, which is this potential, the real part of the potential, and also the imaginary part, which is called the rotation number or Johnson-Morse function. All kind of names have been used there in the theory of almost periodic Schrödinger operators or random Schrödinger operators. But as a probabilist, thinking about this as the CDF, the cumulative distribution function, which goes from 0 to 1 if you divide by pi. So that's monotone, and on the gaps, of course, it's constant. That's where, and here you see this gap, this big gap is associated to the 1/2. So the question is, of course, is there a gap labeling here? So interesting question, which I have no idea. So the next big gap, for example, is not associated to a small fraction. So it's not clear what is actually happening. But it's an interesting question if you are in the theory of Schrödinger operators. That's what you do. You look at, you know, the nature of the spectrum, what type of spectrum there is, and you are also interested in gaps and of the spectrum. And so density of states, integrated density of states, a very classical Lyapunov exponent, which is the in the Schrödinger case. It's the Lyapunov exponent. Here it's just a real part of a potential. But we want to know that this potential exists when we take the barycentral limit, and it indeed does. And what one needs just to show that it decays fast enough. And in order to show that it decays fast enough, we have to estimate how big the eigenvalues become. How many eigenvalues have a specific size? We need to have control about that. And for that we need that result here, that Mickey Mouse result. I call it a Mickey Mouse result because it's almost obvious. Once you see it, maybe once you discover it and you are given a hint that you should use the Cauchy interlace theorem, then it's just an exercise. The problem is to find it, and I have not found it in the literature yet. But it's a useful result because it gives us explicit bound on the eigenvalues of the Kirchhoff Laplacian. So let me focus a little bit on that here. So everything is actually written down what I wanted to say, but I want to say maybe a little bit more about the theorem, maybe a couple of examples, look at a couple of examples, and then the proof. So about the examples here is kind of one of my favorite graphs, the Davichi graph. It's two tetrahedra glued together, and so what we have is, it's a nice graph because you have integer eigenvalues 0, 3, 5, 5, 5, and there also, so here's the vertex degree. There are two vertices which have degree 3 and three vertices which have degree, the middle, which have degree 4, and so if you look at that, so that's always smaller than 2 times that, so by far. Also here, it's actually quite clear. In this case, it's a cyclic graph. It's an example where we have a sharp case. By the way, all the examples I saw where it is sharp, this inequality, where it really is an equality, is always with the largest eigenvalue, the spectral radius. So in this case, this identity is quite well known in the case of in the case of n of the largest eigenvalue. You can just estimate it's a sum of two self-adjoint matrices, and then the spectral radius is smaller or equal than the sum of the spectral radii. And so you can do that directly. That's sometimes attained. Most of the cases it's actually also smaller. What is very interesting is the proof. So if you look at the proof, you are tempted to use to use a Courant-Fisher or some kind of Courant-Fisher gives you an explicit formula for the eigenvalues as a minimax formula. But related to that is the interlace theorem of Cauchy. Let me just explain how it works. So first of all, you try to prove it by induction. Of course, that's what you do. Induction with respect to the number of vertices of the graph, and then you try take n equal to 1, so that works. That's the induction assumption and the foundation of the induction. And then you make the induction step. But then there is a problem. Of course, you want to use induction and shave off some of the matrix, shave off part of this. But what happens when you shave off this? It's no more an adjacency matrix of a graph. So you cannot use directly induction. And here is something you learn kind of if you listen to mathematicians when you are in college. Of course, the knowledge which you learn in college is just, it's everywhere in the books. You can look it everywhere. But what is the value of a good education is that you are told in class what is important. You're selected what is important, what is relevant, and also little things. And I learned this kind of at one point. It was a little remark of Leuchli. Hans Leuchli was a student of Specker, was a logician, and so I had some logic courses. And so he mentioned once this paradox, that if you are proving something by induction, it's often easier to prove something stronger. And that's a paradox, right? Because if you prove something stronger, you prove something stronger, it also looks as if the proof is harder. But that's not true, because when you do induction and you make an induction assumption, and the induction assumption becomes also more powerful. If the induction assumption becomes more powerful, you can push the induction step with more likely. And that actually happens here. So just the natural thing to do is to expand the theorem to more general matrices, where then it's invariant under this taking principal submatrices. This is a principal submatrix. And if you look at the eigenvalues of a principal submatrix, there's a self-adjoint matrix. There's a general theorem of Cauchy, the Cauchy interlacing theorem, which is not difficult to prove. There's a nice proof of Fisk, Steve Fisk, who I've mentioned here in the context of graph coloring. A big fan of him. He has passed away, but he's one of these mathematicians who kind of make extraordinary things, but they are not recognized for that. So Fisk has a kind of a nice proof. I will kind of maybe write it down at one point, this theorem. And so what you do is, if you take this, now you make the induction step, what happens is if you take a submatrix, I call this M, and now the eigenvalues, they are just n-1 eigenvalues. And then by induction assumption, you have this estimate, because the D's, the diagonal entries have not changed, right? The diagonal entries are still the same diagonal entries here. And so you have still the same estimate. But then because of the interlacing, also the lambda k, the eigenvalues of the larger of the matrix you are interested in also satisfies this. So it's a direct consequence of the Cauchy interlacing theorem. So I think it's completely unpublishable because it's so simple. And so if somebody sees that, of course you are just you don't even if you see that from here, you might not even give credit for that because it's so simple. But that's the thing. So I'm actually pretty proud about this. I like this world, this Mickey Mouse world, where things are kind of simple results, but actually kind of also, intelligible. You can immediately kind of see. And so the Mickey Mouse theorem, maybe this is the mini Minnie-Mouse theorem, which is a little bit stronger, and so there are lots of puzzles, right? Lots of things where we kind of don't know what is really happening. Maybe we should put it here. So that's kind of the puzzle. This is a bone which we understand, but this is really a puzzle here. We have no idea. I've not seen. This is a result from 2015 of mine, that these limits exist, and so this density of states exists, and so there's but I've not seen any work on this. Yeah, this is a two-dimensional case. In high dimension, you see similar pictures. But what is then the main upshot is that this rooted spanning forest, you know, has a limit in the barycentric refinement limit, and also the spanning trees, and also the quotient also makes sense. So you have, so in the one-dimensional case, the omega 0 is 0 because of polynomial growth. In the higher dimensional case, the trees also grow. Two-dimensional, high dimensional, the number of spanning trees grows exponentially too. So also here, this is possible. The potential value at the bottom of the spectrum is positive. So this is a, and you see numerically that the Lyapunov exponent, this potential is positive on almost all points. At this point 4, it looks like if it is 0, but so that would suggest also that the logarithmic capacity, if you integrate over this is the logarithmic capacity, that this is exists and is positive, but I don't prove that that this exists here. So at every point, for example, so it's only away from the spectrum that this or at 0, and at 0 it's just by the fact that this is bigger or equal to 0, and so it's boxed in. So that's what we know. So that's what I wanted to say today.